All right. Thank you guys for joining us. My name is Natalie C. I'm an engineer at Tipping in Berkeley. We're a 39-person firm. We've been around for about 41 years. I've been living in the Bay Area for about 20 years, originally from Canada. Joining us today is 𝗦𝗂𝗲𝗁𝗁, who is one of our principals. A little fun fact about Mike, he has a lot of extracurriculars. He has 3 children. And he also plays the violin, plays
Yeah, the
um
guitar. I do play the
he
guitar.
plays the guitar, and he also rollerblades and plays and bikes. A very active person. So um today we are going to be going through part 3 tutorial. In our session today, we're going to be covering fiber section analysis. And a part of the tutorial is also going to be on plotting a chart from a table of data. Before we dive into part 3 tutorial, we're going to do a quick review of the part 2 session. So I'm going to give Mike a chance to do our review. So I hand over the mic over to him.
All right, great. Thank you. I'll share my screen and we'll get started. So I am showing an example of what we did last time. And this was a way up example. Just to sort of refresh our memory, it's very easy to use Sketchulation to calculate the weights of shapes. We use it to calculate the weights of our floors for our seismic design. And what we did was we pulled in a plan from a PDF. We took a screenshot of a PDF that we got from the architect, and then we traced the shape of the floor with a shape entity, and then we calculated the weight of the typical floor assembly using this table, created a table and filled out these rows, and then we took the sum of that weight column. We got almost 70 PSF, and then we selected our shape, our boundary shape here. We went to modify properties, and we went to the entWeight area, and we entered in this formula here to calculate to assign the weight. We made sure it was an area entity type or element type rather. And we also had some other special assemblies. We had, say, a weight of tile. We drew a couple of areas with tile weights, and we entered the weights of those things. And then we also had a facade weight, and that is this dashed line here. We assigned this in a line element type and gave it this expression W underscore facade. And then we use the entWeight command to calculate the weight. Before, when I first did this, I actually entered in the tag for the boundary shape. We created a boundary around all the stuff that we wanted to add up, and we tagged it with this ship BDY, and that goes inside here in the entity tag. And then we actually we copied this plan, and we made a new layout. And when we go to the next layout, we copied this in here, and we just imagine that we have another floor, but this one doesn't have tile. We have another boundary shape, but this one we put the underscore level 2. So now we have 2 floor levels on 2 different layouts. And I just did a page up, page down to go between the layouts. And then we made a couple of tables for fun. You'll notice that these expressions, they refer to this symbol TG, and that means nothing outside of the table. So if I try to get a result off of this, it would give me a question mark telling me that TG is not a constant, has no assigning expression. So that should be expected because I haven't defined TG, but it is defined in the context of the table. Or I could go outside the table. I could make, I have a different expression system going on here. I could make an example. And this is what we do for our calculations is we'll give an example input so that you can actually see how the expressions work, but then we'll do all the calculations for the variety of things in the table. So if I put in here ship BDY for for this symbol TG. Now I can recover a value. So this is now processing the entity weight algorithm for this particular tag. And I can also get, this was the center of the weight. So you can figure out where your center of mass would be. And we showed how that can assign to a point. So we had it assigned to this point here, so that if the shape of the floor changes, or maybe the tile gets larger, the calculations would update and it would shift that point. I don't know if you can see that. It's a small little change. Um, so we showed all that, and then we made a table where we calculated the weights of these individual floors. And we also showed that you could highlight the contained entities, and you can see what's contributing, or how things are contributing, through a pie chart here. And this is sorted by layer. So we made some layers and put our areas on one layer and our facade on another layer, and then the tile was on a third layer. And then you can look individually at how these the various shapes are contributing. So that was the way up example. Any questions? Anything unclear about that you want to go over again?
That's great.
All right, thank you. Lastly, last week we did talk just briefly about expression systems, and we discussed how if you want to run the same calculation for two different inputs, you would think, well, I could just define, say, a variable twice with two different inputs. But then, if you did that in the same expression system, the global one, then there would be some ambiguity. It doesn't know which value to use for x. So we resolved that by creating a new expression system. That can be done up here with this button, or I like to go to the expression system sidebar. And so these are the expression systems that I have. Global is always there, but I made a new one just with the default name. And then I put this value for x, this expression defining x, on the new expression system. And I have this checkbox here that tells the program to override the layer colors, so I can see what expressions are on which expressions are on which expression system. And then I created a new value for x. And you see here, I didn't have to retype the expression for y. I can just use the request for value operator, and by default, it's going to inherit the expression from the global expression system. Every expression system has a parent expression system, and by default, they're all going to refer back to the global one. But this is a way to provide a hierarchy of how symbols are defined. So y is defined in global, and since that is the parent for XS001, the expression in XS001 is inherited from global. Okay. Any
Perfect.
questions on expression systems? No. Okay. Today we're going to talk about what I think is probably one of the most powerful aspects of Sketchulation, and that is fiber section analysis. The program allows you to do basically concrete cross-section analysis for any arbitrary shape. And so we're going to walk through how that can be done. Last time I did this tutorial, I did it with a column, and so I think today we'll do it with a wall. There are some examples up here that you can refer to later if you'd like. There is a concrete core wall example, and also this column, moment rotation, and PM. Those are examples that use this fiber section analysis, and also a retrofit with FRP. You can refer to that too. These all use the fiber section analysis features. But let's say we're going to design a wall. I can imagine that I have a shear wall in a building. This building right here was a steel frame building, but if it were a shear wall building, it might have a shear wall, say, right here. That wall might be, say, 25 feet long and 24 inches thick. So I started to draw a shape, and I push at 24, comma 25 feet. You'll notice that I put the apostrophe to signify feet, but I didn't put anything for the 24, so the default would go to inches. And that's controlled in the layout properties. You can change those units, the default units, if you like. And so this is my wall. I'm going to change the layer of that. I'll go ahead and start using, maybe I'll just use the default layer and I'll do the paintbrush to apply to that. And I see actually my wall could be a little bit longer. I'll make it another a few feet longer. And I'm going to use the snapping command to snap to a particular rounded distance. So I don't have some random distance. I'll type, I could have typed 0, but I'm going to set my rounding distance to say 6 inches. And now as I'm lengthening it, it's doing this in increments of 6 inches. So I have this wall that I'm going to work with. I'm going to dimension this so I can see it. You see it's 29 feet long, and maybe I'll give it a hatch pattern, HP, and I'll make it solid. So this is my wall that I'm going to analyze. I'm going to select this. I'm going to copy it, Control C, and I'll go over to my new document here and push Control V. And here we have it. And, this fits nicely on the page, although for my section analysis, I'll probably want to make this somewhat bigger. So I want to make my page smaller relative to the wall, so the wall takes up more page space. And so then that means I'm going to want to decrease the annotation scale. So I think maybe 48 would be a good guess. So I put that in there, and I see that fits pretty well. This will be a nice calculation page. So I'll go over here and I'll type a little text, and I'll say this is my wall flexural uh, capacity or something like that. Maybe that works for me. And I give that the heading text style. And I'm good to go. By the way, if you have any questions, feel free to just jump right in and interrupt me if anything's unclear, if I'm moving too fast. Okay, so I have my wall here. What I need is some reinforcement. So there's a couple ways I could do this. One of the things I could do is just place reinforcement by hand. So that is RBS, rebar section. And so by default, I'm putting in a number 8 bar. Maybe I want to put something larger like a number 11 bar. And let's say I want to put that bar offset from the corner a couple of inches each way. So what I'll do here is I'll type B for base point. And now it's asking for a new base point. That's going to be the corner of my wall. And now you see the command is working from that base point. And here I type the @ symbol. And then let's say I want that to be, this is the center of the bar, is going to be 3 inches each direction from the two faces. And now let's say I mirror that, MIC mirror copy. I snap to the midpoint and copy that up. And now I have a couple of bars. And then let's say I'm going to do 4 bars on this face. I'm going to use the array command, AR, array linear. And what I want is a quantity plus extents. So my quantity, it's asking for the number of copies. So I want to want 3 copies, but then this last one, we'll go ahead and omit that. But in order for the spacing to work out, I want to enter 3 copies here. And it says, do I want to ask me if I want to omit the last one? I say yes, because I already have that bar. And it's asking me for the base point, which would be this one here. And now I just lay out these guys. I type S to get to the insertion snap. And now I have my bars defined there. And then I'll go ahead and array those this way. I'll do exact spacing, 6 inches, and I'll just lay some bars in until I get something that looks nice. Okay. So that is my bar layout. And then let's say I want to put in my ties because maybe I want this to look nice and eventually end up in my design. I'll type RB, this time not the S, but just the regular RB. So this will give me a rebar and elevation. Let's say I'm going to need number 5 bars. It's a stirrup, so it'll use the stirrup bend radii. And I'm going to hook it at each end like that. And this is cool. I can just snap to the bar and it's going to wrap around these bars as I draw my cage like that. Okay, so quickly there I have my pattern. You'll notice that the lines are sort of intersecting. That's because of the thickness of the layer, and that can be adjusted. You can also type in the thin lines command, and there you see that none of the layer thicknesses apply. So now you can kind of see exactly where things are laid out. But for graphic purposes, you normally do want that thickness to show, and so that's how we'll leave it for our final print. So I have my one boundary here, and then let's say I just go ahead and mirror that, MIC, mid, like that. And so now I have my boundary that I'm working with. Now I said there were two ways to do this. I could have done another command, this concrete column command, ccol right here. And here's maybe a quick way to draw a boundary. Maybe I'll start with an 8-bar boundary and number 11 bars, and I could enter a steel ratio, so some different options for how you might want to do this. But I can simply start drawing here, and this is going to create essentially a column cross section, and I can just do a polar snap. So now I have a square cross section and delete that boundary. And there you go. I have an 8-bar boundary instead of my larger boundary. And let's just say I do something crazy. I leave these guys asymmetric just for fun, even though you wouldn't do that in real design. Okay, so now I've got my boundary bars, and now I want to go ahead and create my field reinforcement. So what I'll do again is I'll use this array command, AR, and again I'll do exact spacing, but this time I'll put in 12 inches. And I just click here and lay these bars in. Now by default, these are going to be number 11 bars. And what I'd like to do is I'd like to know what size should they be if I want a good steel ratio. So let's say I'll make a little expression to calculate this. My row target is 0.003. The code, for a special wall would require 0025, but 003 is slightly better. And so then my bar size or area per foot, well, first my spacing is going to be equal to 12 inches. And my area bar, so A bar is going to be row target times 12 inches. I forgot my thickness of the wall. I'll have to type that in a second. I just put S times TW to be defined in a second. And then times 0.5 because I have 2 bars. So it gives me a question mark to start with because I haven't defined TW. Maybe I just go ahead and make an expression dimension here, XD, and call that TW. And so then now I see that my bar size has to be 0.43. I know from my old memory that will correspond to a number 6 bar. So I change these guys, I grab them all, and I start to type size because I know that's a property of those bars. And I see bar size, enter 6. Oh, 6? There we go. I must have typed the wrong key. Okie doke. So now I have my a nice cross section, very conventional. I know this is buildable, and now this is kind of what I'd like to start with my architect friend, and see if this will work for the demands from my building. I have this dimension here. It's 29 feet long, so that's pretty good. Okay, next thing I need to do is define the materials. So, and for that, I'll go ahead and I'll set this calculation over here, and I'll define my concrete strength. For a wall that's working pretty hard, we would say that might be like 6 KSI concrete. So F prime C, 6 KSI, FY, typically 60 KSI. And now I'm going to make a couple of materials, fiber material right here. Brings up the sidebar here, and I'm going to start with a new material. Now, by default, it's going to be a generic material, but we have some macros to make things go a little quicker. But if you use a generic material, you have some options. You can take a look at the fiber material properties image, so that gives you key to what you're doing. Density, elastic stiffness, Compression, oops, I gotta close this, I guess. Um, Compression or tension, because this is a symmetric material, but it could be asymmetric. And if I do asymmetric, then I can enter all these things for compression and tension. And then you have a pre-strain that can be an expression. So when you see this little pencil, that means it can be expressions, while these are just straight numbers. And uh, the all of these things will feed into our analysis in a second here. Now, if that's a generic material. Like I said, I have some macros here that I can choose from that speed things up, so I don't have to fill out every last little one of those numbers. So this will be, say, a concrete material, and instead of 4 ksi, you see this as a pencil. So that means it's an expression. I can actually refer to f prime c that's defined in this expression over here. So that is going to reference, and you see in the name it references f prime c is equal to 6 ksi. I can take a look at that material graph, the backbone curve, and I can see how the program is modeling that type of material. Concrete also has a creep um, uh, modification to the material that's used in structural analysis, but the typical fiber section analysis is going to use the nominal backbone curve. Similarly, I can create a steel material, and here I would pick the mild steel, and again, I can put in Fy. And I graph that, and I see, okay, there's my steel, there's my concrete, there's steel and concrete together, and I have working materials to use. So first I want to paint this shape with the concrete. So I select the concrete, push the paintbrush, and then select the shape. I push enter, and down at the bottom you see it says material, this name applied to one entity, so I'm good with that. And then I also do the same thing with the rebar, do the paintbrush, and now I just select. Be careful not to select the shape because we don't want a big massive steel shape. And we apply to our rebar. And if we're worried that we did it right, we can override layers and we can see the different colors. Sorry to those of you who are colorblind, but this is the way we can tell between the different materials. Okay, so now I have a wall that I can use for analysis. If I want to really study a cross section, what I would do is say bring up the moment rotation curve for this wall. That is a built-in command. So I type mr and I bring up the fiber section analysis form. And you can see to start with, it's using a very coarse mesh for the concrete. Then you see each of the individual bars are in the mesh. You can select these elements just by clicking on them, and you can select the graph. You can see the stresses in your various fibers. Each of these is a fiber, and when you click on it, you can look at where that fiber's response is on its stress strain curve. So if I click on a bar, it shows a different stress strain curve than the concrete, and I can see this bar is slightly under compression. And this actually might be good enough for design, this mesh, but if I wanted a finer mesh, I can do that. The benefit of having this coarse mesh is that it runs fast, and you always want to find the mesh that is as coarse as possible, but as accurate as necessary. How about that? But let's say I want a better mesh. I go to the mesh options, and you can see it's targeting an element size of 17.4 inches. Maybe I prefer that to be 6 inches. I put in 6 there. I have some other options here which do different things. I can go through them very, very briefly. The meshing algorithm will coarsen shapes. This doesn't apply to a rectangle, but if you had a very complex shape, it does some initial coarsening of that shape so that the mesh doesn't get out of control. There's a few different refinement options, just uniform or near points or none. So when the meshing algorithm runs, it creates an initial mesh, which is very coarse. It's the most coarse possible. And then it goes through a refinement step. And the uniform is going to give you probably the best uniform mesh, but the near points basically does tighter meshing near edges. Regularizing the mesh, what this will do is go around the shape and add seed points to start with, which will give you a better initial mesh and lead to a more regular mesh when the uniform refinement goes through. And then you can decide if you want it to stay with 3 node elements or 4 node elements here. In this dialog, you can also choose a different center point than the default. The default would be at the centroid of the section. And you can decide if you want to change the hinge length factor. This is a factor that gets applied to the dimension of the cross section to convert curvatures to rotations. So, for example, there was a tooltip that showed up, and basically 0 would just give you a curvature graph, and something else will give you a rotation graph. And you can rotate the axes if you wanted to. So I've got all that, and if I wanted to reselect the entities, I could do that here. I can click Create Mesh now, and you see it refined that mesh further. I doubt that it changed the result all that much, but now I can kind of see what's happening as I go through different fibers a little bit better. You can also get this graph here of where the forces are, how the forces are being applied at different locations, and you can see how the shear flow is accumulating in the cross section, and essentially a moment diagram and integration of that shear flow. Okay, so this is my moment rotation curve for this cross section. The assumption here is that there is no axial load. Typically, that's not the correct assumption. There should be some axial load on this, and that's very easy to add in this program. You can go to the analysis section, and you have some options there where you can specify, the rotation range for the analysis, the number of points, and whether you want axial force. Maybe this wall is pretty decently loaded, so I put in negative 1,000 kips. Negative would correspond to compression. I can also analyze at different moment axis angles, which is not really applicable to a wall, but I could do that here by entering in other axis angles. I click Analyze, and now I have 2 moment curvature diagrams, or moment rotation diagrams, rather. One for this would be the 0 axial case, and this would be the case with 1,000 kips in it, and you can see that in the legend. If you wanted to take this data and move it somewhere else for further analysis, you can right-click on the graph, and you have some options to put the data in the clipboard, or save it, or export an image. Also, for a given state of the cross-section, you can click this little scissor button. Oh, and I keep meaning to fix that tooltip. That's not quite correct. But anyway, when you click this button, it's kind of cool. It creates shapes in the drawing with those colors of that you were seeing in the other image, and they're on a specific layer. So I'll isolate that LAI, and then I can move them off to the side, or delete them if I want to. So I isolated them, move them off, and I can just keep them there if that's helpful for me for a plan checker or whatever. So there's that's one of the options that's available to you, and you can kind of start to see what happens. What I like to do is sometimes I'll use the arrow key. I'm just holding down the arrow key left and right, and you can kind of start to see what happens as we start to lose strength. The fibers here are getting beyond their strength loss strain of 0.003 and starting to descend. So that all makes sense. At the same time, I might be interested in what's going on. Yes, and I see the rebar is also losing strength. So the 2 of those together are causing this dip. Other analyses available, I can do a PM diagram of this wall, and here we see this would be the nose of the PM diagram. We see it's asymmetric as we expect because I put in asymmetric reinforcement, and again I can arrow around and see the graph do its thing. You'll notice I'm plotting. There's a cap up here. This is a reduced PM diagram, reduced for the code phi factors. I can also plot the unreduced. So here you see the cross-sectional behavior without the phi factor being applied. And if I'm interested in what these actual numbers are, that data is included here in the text box. And then lastly, there is a moment graph. You can see it's not very interesting for a wall because there's very little moment in one direction and a lot of moment in the other direction, but that's available. It's, useful for columns and things like that. Okay, so that's the summary of fiber section analysis using this form. Are there any questions, anything you'd like me to elaborate on? Nope.
Looks good.
Alrighty. Yep. Okay, so this is what you would do if you're really trying to dive in and study a cross section very carefully. If let's say I was really struggling to get this wall to work, and I decided, really in order to get it to work, I'm going to have to really increase the moment strength, and so I go crazy with it. I change these bar sizes to number 18s. Okay, so now they're very much larger. And then I turn all of the layers back on again. I go back to my fiber section analysis form, and then you'll notice that it already updated it. It redid the analyses with this new mesh. And the key thing to notice is that the diagram looks very much different than it did before. And it's no longer very different between the case with zero axial load and negative 1,000 𝗂𝗃. And what's happening here is that we're creating an over-reinforced section. So you can over-reinforce a section with high axial load, or you can over-reinforce it with reinforcement. And what that means physically is what's going on is you're getting onset of strength loss in the outer fibers of the cross section at a lower rotation angle. And so it's just descending, and that neutral axis is drawing further and further back as you destroy the concrete. At the same time, the rebar at the other end is not getting to that strength loss point. So some of it is, at the peak moment demand is just barely yielding. So you have a very large compression zone. That compression zone, you can see it visually where the neutral axis is, and you can also have it reported right here, 81.8 inches of compression zone at this state. So this is useful, for really studying a cross section and trying to understand whether it's doing what you'd like it to do as a designer. Other things you can do with this program that are kind of cool. Let's say I want to take into account confinement. I can draw a rectangle here, REC, and I snap to the insertion point, and then again S. So now I have just a rectangle, and I go up here to my material editor, and I create a confined concrete material. And again, I'll put in the same F prime C that I had before, but the confinement is going to strengthen that to 7.2. We can see what the confined versus unconfined concrete looks like. I get the green graph with my confined concrete, so that's both stronger and it's more ductile. And so then I just assign this material with a paintbrush to this shape, and I can override layer colors and see that it is there. And then I can do the same thing, just do a mirror copy here like that. And so now I have that same confined concrete here. Then we go back to our fiber section analysis form. In this case, I do have to reselect the entities. So I click the button, I reselect everything, push enter. And now we see we have this confined concrete zone, and we see that our ductility actually improved a decent amount, and we see different stresses developing in the different materials. So here's my confined concrete, and then outside the confined concrete, I'm seeing the cover start to crush. And then as we push it further and further, we see that the confined concrete still hangs on, but then the rest of the concrete is sort of dying and going away. Okay, so that's the fiber section analysis in this very detailed form. For design of a single wall, you might do this. You might really dive in deep and get this detailed type of analysis. For most of the time, you are going to have a lot of different walls or a lot of different cross sections that you need to design. And Sketchulation has some really powerful features for being able to design things in mass. So one thing I can do here is I can tag this cross section and I can get the moment curvature diagram or moment rotation diagram that we see here. I can get it through a function. So what I'll do is I'll tag, start to type tag, and I see here it says entity tag right there, that guy. And let's say I call this my XS wall. I click OK. And that assigned that tag to that outer shape there. And then I can make an expression that says MR is equal to get, start to type get, and what I want is m theta. And now it's going to ask for a cross-section boundary. I type in my XS wall, and I push the request for value operator, and it generates my moment curvature diagram as an array. I can have that array not display all the numbers by starting to type, I select it and I start to type render arrays compact, say yes. And so now I can see that there's a result there, but I'm not displaying all the numbers because who wants to see a bunch of numbers? Now there are other options in this function as I look at it. You can see at the bottom right, there are 5 different overloads to this function, different versions of the function that all require different inputs. And I can scroll through them with the arrow keys here. So I can see that the next version adds an argument for bending axis angle. Another one adds an argument for axial force. And then mesh size. And then finally, I can indicate whether in more information about the rotations, the starting and ending rotations for the analysis. So all these features exist in this function, but for now, probably I'll just stick with the version with the axis angle and the axial force. So I'll put in here, I'll put a comma, and it automatically increments to the next argument. This would be 0. And I want to put in that negative 1,000 kips. Okay, so now I have my moment rotation with the negative 1,000 kips, and it's stored inside this variable MR. Now, of course, I want to plot this, so I will copy my page, Control CO, copy, and come over here. And now we're going to make a chart. So CHT is the command to make a chart. I'll snap there and go to the sort of the halfway point down the page. And then I'm going to add a series. SER is the command, add series. And we're going to go over charting in session 5 in great detail, but we're just going to give a little primer on it right now. There are several different types of series you can add. We're going to be adding this table vectors. I'm sorry, not table vectors, but vectors type of series. Vectors means basically it's an array of data. So we have or 2 vectors of data. And I can see here are the fields I need to fill out. The expression for the x data or y data. And there's a checkbox here where if you have both x, y in one array, that you can just use the x field. So that's what I have in my case. So I pick MR, and that's all set up. I click add, and it creates my moment curvature plot on this chart. And you can see there's these the numbers go from plus 2 million to minus 2 million. Those would by default be in kip inches, but you can force it to be in kip feet if you wanted. So what I can do is, let's say if I want to make sure I know the units of this, I select the chart, and you can go to modify properties, and you can see that for the axis Y, I can specify units. I could have done that very quickly just by selecting the chart and starting to type units. And you see both in the sidebar, it's filtering out anything with units or keeping in anything with units in it. So I can see it there. I can also see it in the left here in the little list. So I want Y options, units, and I'm going to enter in the units I want. Kip, feet, like that. And now it's taking the data, whatever units it's in, kip feet, Newton meters, whatever the base data is in, and it's converting all of the points to kip feet for you on the fly. So you don't have to create another table and do some units manipulation or anything like that. And then I'll double click on this and I'll type that in as my title. This is moment, right? And then on the bottom, these are rotations. So I double click on that. I type rotation. And then the chart also has a title. If I select the chart and I find the place where it says title, I can select that and say moment rotation curve. Okay. And so that is my moment rotation curve for this cross section under a demand of 1,000 kips of compression. Any questions on any of that? Okay. Now, keeping going, I can go back to my original design. I can change these bar sizes back to the number sixes that I had. And you see it reran the analysis. Took a second because it has to remesh that entire cross section. And I can change my boundary bars, select all these guys here, and start to type bar size again, and put these back at 11s. You can see the question mark shows up a second, and then it does the analysis and creates the graph. Okay. Any questions on the fiber section analysis or the graphing so far?
Okay.
Okay. Now, let's say you have a couple different conditions. Maybe you have one of these walls that has 1,000 kips. Another wall has, say, 2,000 kips. So I'll go in here, I'll put an underscore and say this is MR1. And probably I want a phi factor on this. So there is another function, get phi m theta. Okay, so that's going to be a phi factored moment rotation curve. And now I'm going to copy this, Control C, and it's asking, since I changed the symbol name, it's asking if I want that to replace everywhere where it was being used. And typically you do want to do that, so that'll make it so the graph updates without me having to go in and fix it. So I click yes, and that's taken care of. And then it makes a new expression, and this one I'm going to call 2. And let's say this has 2,000 kips, even more. Okay, so now I have these two moment rotation graphs, and I'm going to bring up the series editor here to add the second series. So I type edit, start to type edit series, and there it is there. I just have this one burned into my brain, EDS. And it brings up the series editor. So here we can affect multiple series at once, multiple charts at once. You can select multiple charts with multiple series and change their appearances and all kinds of things all in one place. What I'm going to do here is right click on that. I'll say duplicate series. And it asks me some information. You can do some finding and replacing as you duplicate the series. I'll say no for now. I'll double click on this series, and I want this one to be MR2, like that. And you see it created the MR2 for me. This one did not update with the replacement, so I have to go back and look at why that is. But now I have both of these moment rotation curves on the same graph, but I want to differentiate them. So I wanted to talk a little bit about the series styles here, all the options that you have. So let's just go through some of those options quickly. I'll do the first pull down here. Well, first, before I even get to that, you can filter names. So these happen to be very similar names, so it's not very compelling, but if you had many different series in this list, you can filter them out and get what you want quickly. You can also filter properties. So, if I'm interested in the line properties, for example, I just start to type line and I get to this. And let's say I want this to be, thicker line. I put in 3 there. So it's thicker. I can change the line type if I want this way. So that's how the filtering works. Now, under the general drop-down menu, here's where there's a lot of summary information, and I'll briefly go through these. The most important one is right here in the top, the colors. So you can change, say, the hue of a series just by clicking that H button, and it's not going to change its saturation or its sort of luminance. It just changes the hue component. So that's a nice way to select multiple series at once and have them all be of the same sort of color family. At the same time, I can select them both and just affect their saturation. So now I'm not changing the hue, but I am changing the saturation. And I'll go here and maybe just lighten them up a little bit. Okay, so that's how these different buttons work. You'll see that there's marker edge, line, fill, and marker fill, and we're not showing any markers, but why don't we go ahead and show some markers? So you have the option of selecting a marker symbol here. I'll do a circle for that one. Maybe I'll right click and I'll actually enumerate markers. So one is symbols and I mean, sorry, circles, and one is diamonds. And maybe I don't want every single dot to show up, so I can tell that evenly spaced, but maybe every fourth dot, something like that. Or I can just have it only put the marker at the maximum absolute X value, which is way over there. Probably not that one is what maybe I'd want extrema or something like that, or maxima. So now I'm kind of seeing, they're identifying those series, but it's not so many dots. Okay, so then also you can have point labels in graphs. And what's cool about the point labels is that you can put in fields that will read data from the graph. You can read, table data if this was a table series. You can read the XY data for a particular plot. And in my case, I'm really interested, let's say, in the peak moment. So I can put in here. First I want to do is I want to make sure that this is set to maximum absolute Y. And then I put the caret and Y like that. And now it's showing me my peak moment for these two graphs, just like that, at the maximum absolute Y location. So now I've kind of talked about a little about the colors. Notice that these are all the same hue. The marker, the line, and everything is all following the same hue. And that's controlled by these checkboxes here. I can choose to have them be different hues, but by default, they're kind of all coming together. So you don't have to worry about changing different colors for different components of your design of the series. There's a few different options for special things where you can do stepping and histograms. And then you can also fill, say fill to the x-axis. And by default, that fill is going to be an opaque fill, but I can go here to the fill tab and I can change that to be not opaque with this alpha, the transparency component. Okay. Series are part of an expression system. So these arrays are part of the global expression system. But if I had different arrays on different expression systems, I can control where the series is getting its information by setting it here. I talked about lines. I talked about markers. Yeah, I think that's pretty good for now for today's purposes. Any questions on the graphing or anything like that? Okay, I think that's all I was planning to cover for today, and we're about 5 minutes early, which is perfect for me
That's
to get
great.
on to my next meeting. And so if there's no final words, we'll just wrap it up and wish you all a good day. And I'll say also if any of this, if you have any questions along the way, if there's anything you want to see, want me to expand on anything for next time, just please do send us a note. We're always happy to hear from you and tailor our presentations to what you're interested in.
Great. Thanks, Mike.